Okay, so problem number 1 is on bacteria culture. A certain culture of the bacterium Streptococcus and initially has 10 bacteria and is observed to double every 1.5 hours. So we want to find a model for part A. Find a model n of t equals n sub 0 2 to the t over a. And that's going to be for the number of bacteria in the culture after t hours. So we need to look at the first part. It says initially. So whenever we see the word initially, that's our n sub 0. So n sub 0 is 10. And it says it's doubling every 1.5 hours. So that's A is 1.5. So n of t equals 10 times 2 to the t over 1.5. So that's part A. Now for part B. Estimate the number of bacteria after 35 hours. So we're going to plug in 35. So we have 10, and we have 2 to the 35 over 1.5. So I'm going to plug this all into the calculator. So 10, and then I have 2 to the 35 divided by 1.5. And we are going to get, so a pretty big number here. I think in the back of the book I was looking that they wrote it out in scientific notation. I think it depends on what your teacher wants, but this is actually more exact than what they have in the back of the book. And then for part C, when will the bacteria reach 10,000? So basically we're asking ourselves, n of t equals 10,000, and we're saying what is t going to equal? So we go back to the original equation and we set 10,000 equal to n of t. And we have 10 and then 2 to the t over 1.5. Okay, so we want to isolate the 2 to the t over 1.5. So the first thing I'm going to do is divide both sides by 10. So that gives us 1,000. And 2 to the t over 1.5. So if you remember when we were talking about earlier, that you need to take ln of both sides to get the exponent moved, because whenever we have a variable in the exponent, right, we want to move this to the front. So the t over 1.5 moves to the front of ln of 2. Okay, now I'm trying to isolate the variable. So if I just take this whole thing and I multiply, so kind of picture that this is, you can put the ln of 2 in the numerator, so I kind of have like 1.5 over ln 2 is what I end up multiplying to both sides. So I have t is going to be, so I have 1.5 divided by ln of 2, and then I want to multiply that by ln of 1,000. And we get about 14.9 hours. So 14.9 hours. Okay, next one is number 5. So number 5, the fox population in a certain region has a relative growth rate of 8% per year. It's estimated that the population in 2005 was 18,000. So for part A, we want to find a function n of t equals n sub 0 e to the RT that models the population T after the year 2005. So we have N of T. So if we read it, it says that it's estimated that it was 18,000. That's our initial population. E, so it says 8%. We just need to write that as a rate. And then T, so that's part A. Now for part B, it says use the function from part A to estimate the fox population in the year 2013. So if we started in 2005 and we go to 2013, that's going to be 8 years. So we have N of 8 equals 18,000 e to the 0.08 times 8. So we're going to type that in. 18,000 times e to the 0.08 times 8. And we get about 34,137 if we're rounding for population. Now for part C, it says we want to sketch a graph. So for part C, remember we had this equation. Okay, so we want to graph this equation. So kind of considering if we start here in 2005, I'm just going to increase by every 2 years. You know, it doesn't really matter all that much. So here's 2011. So it just says specifically from 2005 to 2013. And then I'm going to count by 10,000. Because I know that I started out at 18,000 in 2005, and I end up at 2013 at about 34,000. So about here. And then we can actually plug in these other values, and like for 2007, I think we get like a little over 20,000, like 21,000. And then here goes like that, and then a little bit higher, almost 29,000. So here is that graph. Number 9. So number 9, we have a population of a certain city is 112,000 in the year 2006, and the observed doubling time for the population is 18 years. So for part A, it says find an exponential model. So N of T equals N sub 0 to the T over A. So we have initial amount was 112,000. And then it says it doubles every 18 years. So that's part A. Part B says find an exponential model. So now, what if we want to use this continuously? And so first we need to find R. So if it's going to double, so think, 224,000 would double it. You'll notice in a minute it really doesn't make that much of a difference what we have. And it says it takes 18 years to double. So when I divide both sides by 112,000, I'm going to get 2. So no matter what, when I double, it's going to be 2. If I triple, it would be 3. So we want to solve for R, which is in the exponent. So I want to get that out of the exponent. So I'm going to do ln of both sides. And then I need to divide both sides by 18. And just to save some time, we get R as 0.0385. So now we kind of take this information here, and we plug it back in. So we have n of t equals 112,000 e to the 0.0385 t. So that's B. Now, for part C, we want to graph that. So I'll do it down here. So this is 9C. So we have started out in 2006. So remember, every 18 years it's going to double. So like 2024 it's going to double, and then 2042 it's going to double, and then 2060. So I'm just adding 18 years. So I'm going to rate by the thousands just to save. So like I'm going to start out like here's 112,000, 224,000, 336,000, 448. You don't have to do those same numbers. And I'm just going to go all the way up here just to save some time. You can keep going that way, and there's 896,000. So in 2006, we start here, and then that doubles, so here, and then that doubles, so here, and then finally that doubles. So here's our exponential function. Now for part D, we want to know when will n of t equal 500,000. So I'm going to set 500,000 equal to 112,000, 2 to the t over, is it 12? Yeah, I think it was, no, it was 18, right? So we're going to divide both sides by 112,000. So we get, just to simplify, it's 125 over 28 equals 2 to the t over 18. So now I'm going to do ln of both sides. Again, that just moves the t over 18 to the front. And now I want to multiply. So I want to isolate t. So I'm going to multiply by 18 over ln of 2 to get those to cancel. So 18 times ln of 2 here. And let's see what we get for that. So I have 18, divided by ln of 2. And we want to multiply that by ln of 125 divided by 28. We get 38.85. So 38.85 years. Number 11. Not 11.
Who got kind of speeds?
So number 13. Number 13, bacteria culture. A culture starts with 8,600 bacteria. After 1 hour, the count is 10,000. So for part A, we want to find a function that models the number of bacteria, n of t after t hours. So we want n of t equals n sub 0 e to the rt. Okay, so in order to do this, we need to solve for r first. So I know there are 10,000 after starting with 8,600, and that's after 1 hour, so that's 1. So we're going to divide both sides by 8,600, and that gives us just reduced 50 over 43. It's going to be e to the r. So now I'm going to do ln of both sides. So we just get r on the right side. And when we plug that into the calculator, we get 0.10508. And now we can go back and rewrite the equation. So n of t equals, again, our initial amount was 8,600 e to the 0.1508 t. So that's part A. For part B, we want to plug in, so for part B it says find after 2 hours, so plugging in 2, we're going to use that previous problem, that previous result, and we're going to plug in 2, and we get about 11,628. Again, just type that into the calculator. And then for part C, after how many hours will the number of bacteria double? So if you remember from the previous problem, basically whenever you double, it doesn't matter what you start with, it's just always, when you divide, you're always going to end up with 2. So we're going to take ln of both sides. So ln of 2 is equal to 0.1508 t. And then we're going to divide both sides by that decimal. And we get about 4.6. And this is hours. So for number 17, we have radioactive radium. The half-life of radium-226 is 1,600 years. Suppose we have a 22 milligram sample. So for part A, find a function m of t equals m sub 0 2 to the negative t over h. Model, so we want to find that model. Okay, so we have m of t. So our initial amount was 22. And then it's going to be 2. And then it's negative t over 1,600 is the half-life. Okay, for part B, now we want to find a model, but using the one with e, so it looks like this. It's m sub 0 e to the negative RT. So we have, again, this is going to be half-life. So we want 1/2 equal to e to the negative r times 1,600. So we're going to do ln of both sides. So we get ln of 1/2 equals negative 1,600 r. We're going to divide both sides by negative 1,600. We get r is equal to, so we get a really small decimal, it's 0.0004332. So here's my function, it's m of t equals, our initial amount was 22, e to the negative 0.0004332. So that is, that's going to be the answer for B. Now for C, how much of the sample is left, or sorry, how much of the sample will remain after 4,000 years? So we want to do m of 4,000. Now I just plugged into the first formula. It wouldn't vary too much from the answer that we got in part B, but I figured the first one is what we were given, so I used that equation. So we're literally just plugging in 4,000 in for t, and we get about 3.9, and that was milligrams. For D, okay, So after how long will only 18 milligrams of the sample remain? So we have 18 is what we end up with. We started with 22. So this is the equation we want to solve. Again, we want to isolate that exponent. So we're going to get rid of 22 first. So I have 18 over 22, which just reduces to 9 over 11. And again, the same thing that we have been doing, we're just going to do ln of both sides. So I'm going to move the negative t over 1600 to the front. And then I want to isolate the t, so I'm going to multiply both sides by a negative 1600 over ln of 2. So a negative 1600 here over ln of 2. So again, the ln of 2's cancel, the 1600 cancels. So I get, for C, I get about 463.2 years. So okay, the last one. So for the last one, finding half-life. So if 250 milligrams of a radioactive element decays to 200 milligrams in 48 hours, find the half-life of the element. Okay, so I'm going to start with this equation. Since it's half-life, it's this formula, the negative RT. So again, what we need to do is we need to figure out R first, and then we'll go from there. So again, it said 48 hours. So the first thing we're going to do, okay, so the first thing we're going to do is we're going to divide both sides by 200. So I get 1.25 equals e to the negative 48r. So now we're going to do ln of both sides. So you just get negative 48r on the right side. ln of 1.25. And then we want to divide both sides by a negative 48. And we get negative 0.0046488. You gotta kind of round a lot, or you can even store your value. So for like example, I know you don't do a lot of calculator problems, but if I did negative ln of 1.25, and then I divided that by negative 48, I press enter, I get this decimal. If you go down here to the store button, and then I can store it in as x, and so when I have to use it later within the problem, I can just press this x, t, theta, n. This is just your variable button, and you'll get to it. Okay, so back to this problem. We're still not finished because we want to do the half-life. So remember, half-life, we're going to get half of what we started with. So we want to figure out how long that's going to be. So I'm going to do ln of both sides again. And then I need to divide both sides by that big long decimal. So this is where I was saying, if I didn't want to have to type that all in, I could just do ln of 0.5 divided by x, and I get about 149. And that's like 0.1, so about 149, I believe it was, hours. And there you go. There's your 4-6.